Hi everyone. Today we are going to discuss about a concept called Huffman coding. Hope you people use this, maybe knowingly or unknowingly. Especially the persons we are working in technical field, definitely they have used this concept. So about the students, you also maybe use this concept, maybe unknowingly. Let us see what is this Huffman coding technique. Okay. See, this Huffman coding is the concept used to do compression. So we know that what is meant by compression. Assume we want to send some large amount of data, a large sized file we want to send. Assume we are sending through the mail attachment. So it is not possible to send that large amount of file, that's data. So at that time, what we will do generally, we will compress it. Okay, that means we'll use some zipping or some RAR file we'll use, right? So that means first, so whatever the data we are having, that much we are compressing, and then the compressed file we are sending. So then at the receiver side, again they have to decompress it in order to get the original file. So now assume I'm having a data of one file of size 1 GB. But 1 GB is sometimes not possible to assume. So what we will do, we need to that 1 GB, we need to know where to reduce the data. Okay, so now if we reduce the data, so we need to reduce the data in such a way that we should not get any loss of the data information. That means whatever the information we are having that 1 GB, that means that we need to reduce it to around, for example, 0.6 or 0.65 GB without losing any of the information. Okay, that is the concept of called compression. So the one technique, okay, generally popularly used one technique is called, what is that? Huffman coding. So this Huffman coding is a lossless compression technique. Okay, so lossless means when we reduce the size of the file from 1 GB or whatever to the smaller size, so the original data will remain same, but only the size we are doing. That is the beauty of this concept. Okay, so let us discuss with the help of some examples. Okay, so here this Huffman coding, what it will do, it will assign some code to every character what we are using in the data. So generally, one of the characters we may use the characters A to Z. It may be an uppercase letter or lowercase letter, or it may be the digits 0 to 9 or special characters. So for each character, so it will assign a variable length. So it will assign a variable. That means for the characters which are used so frequently, for that character it has shorter length code, and the character which is not frequently occurring, means least frequently occurring, for that type of character lengthy code. Okay, for example, assume now I have typed hi dad. That means assume I'm sending some message to my dad. So I'm typing hi dad. Okay, let us say I send hi some space dad. This is what the message I sent. Is it this message as it is which will go in the media? Never. So this is going to convert into digital. Okay, for each character, we know that there will be one ASCII character. Okay, every character is assigned as having one ASCII value, that we know that. Okay, so we know that ASCII value of what? ASCII value of capital A is 65, capital B is 66, and goes on. Okay, so now this 65, now we are going to convert it into digits, okay, bit binary. So that is, for example, 64, 32, 16, 8, 4, 2, 1. So 7, 8 bits. So this is what 65 in binary. So when I typed A, capital A, instead of A, this will be replaced by this. So every character is having how many bits? So for every character is having one ASCII value, and that one ASCII value is of what? 8 bit. So what are the characters used? For A, we know that 65, that have written in the binary. Similarly, for D it is 68. For D it is, so for H, ASCII value is 72, I 73. Space, what I am having is one space. Space is also one character. It is also having one ASCII value. ASCII value of space is 32. Let us decode this one. H. H indicates, for H, I will write for H 72. That means 64 64, 32, 16, 8, then remaining are zeros. 3, 6, 7. Okay, this is what H. Okay, this is what H. Then I. So I, for I, it is 73. So there is 0, 1, 00, 1, 001. This is I. So then space. Space is what? 32. 32 means 128, 64, 32, 1, 2, 3, 4. So then what? This is for H, this is for I, this is for space. For D it is 68. D it is 68. 68 means 64, 32, 16, 18, 4, 2. Okay, this is what D. For A already written 0, 1. For A it is 0, 1, 1, 2, 3, 4, 5. Then this one, this is 1. Again D. D is 0, 1, 000, 1, 00. That means, see actually how many characters we typed actually as a message. As a message I typed 1, 2, space is 3, 4, 5, 6. For 6 characters, it will be, data will be sent 6 into 8. 8, it's okay, 8. 48. 48 bit is going to send. But instead of 48, is it possible to send the same message, hi dad, in the lesser number of bits? Yes, it is possible with the help of what? Huffman coding. This Huffman coding, what it will do, instead of sending the same data using this 48 bits, so it will reduce the number of bits. Okay, that is the concept of what? Huffman coding. So this is Huffman coding. So that is what lossless compression. So now let us discuss this Huffman coding with one example. This is the given problem. So in this example, I have taken simple 6 characters A, B, C, D, E. And this is an underscore. And this is the characters what is appearing in my text. For example, that means assume I am using only these characters. And probability of occurrence of character is 0.5, that is 50%. Probability of occurrence of character B is 35%. Probability of occurrence of character C is again 50%. Probability of occurrence of character D is 0.1, that is 10%. Probability of occurrence of E is 40%, that means 0.4. 0.4, that means similarly probability of occurrence of this underscore is 20%, 0.2. So this is what the given problem. Now Huffman coding, now it generates code for A, code for B, like it generates code for each and every characters. Okay, so for that first we need to construct one Huffman tree. Okay, so that Huffman tree, what we have to Huffman tree, so whatever the probabilities are there here, that probabilities I'll sort it. Okay, sort in ascending order. So if I sort the probability in this what order, in this ascending order, which is the minimum list 0.1. So I'll write 0.1. So this is of which character? 0.1 is D. So next minimum is 0.2. 0.2 is of underscore. So then after 0.1, 0.2, next is 0.35. 0.35 is B. So 0.35. 0.35 is B. So next minimum is E, that is 0.4. So next is 0.5, 2 are there, whichever you can write, not a problem. So I am writing A first, then I am writing C. Okay, this is what the individual characters I written in the sorted order. That is in the ascending order I have written. Okay, now what we need to do, so first to you add. First to you add, again if I add what I get, 0.1 plus 0.2, what I get, 0.3. So that again you put it in a sorted order. Okay, so don't keep it that as it is. So now if I'm adding this 0.1 plus 0.2, that is 0.3. That again we need to sort it. Now 0.1 plus 0.2, whatever, 0.3. But in this case, again 0.3 itself is the what? Smaller. So I'll keep here only 0.3. Understood? So again I'll use this 0.3. That means this 0.3 I got. How I got this 0.3? This is not the original value of any of the characters. This 0.3 I got by adding these two. So I'll write like this. 0.3 I got by adding 0.1 and 0.2. 0.1 is of the character D, 0.2 is the character underscore. That means by adding these two, I got this value. Next, as usual, 0.35, 0.4, 0.5, 0.5. So this is B, this is E, this is A, this is C as usual. Okay, so this is my first step. I sorted, then I added the first two minimum, and then again I put it in the sorted order. Now the next step, what I have to do, again you add the first two, so that is 0.3 and 0.35. I'm adding these two, again put it in the sorted order. So if I add 0.3, 0.35, 0.65, that will be the largest number, that I have to keep at last, and these three I am writing first. So the next third step is, so first I will write, so I'll write 0.4 first, 0.4, so then 0.5, then 0.5, then I got this 0.3 plus 0.35, how much? 0.65. 0.65. So 0.4 is of E, 0.5 A, this is C. This is the individual. Now this 0.65 is not the normal value. This 0.65 I got by adding these two. That means 0.3 and 0.35. So again 0.3, again this is the value I got by adding what? 0.1 and 0.2. 0.1 is D, 0.2 is underscore. But this is single, 0.35 is B only. This is single value. This is the third step. Now again what I will do, again fourth step, again I need to add first two I need to add. So if I add plus this one, 0.4 plus 0.5, how much? 0.9. Then again put it in order. So first you write these two and then 0.9 comes, okay? So now after, see here from third step, I'm adding the first two, 0.4 plus 0.5, 0.9. So 0.5, 0.65, so I'm writing this one sorted again, 0.5, 0.65, in decreasing order, ascending order. So I got this one, okay. So now again, I need to add first these two. If I add these two, that means again the fifth step, what I got? In the fifth step, I got 0.5 plus 0.65, how much? 1.15. This is 0.9. So 0.9 comes first, 0.9. So 0.9 I got by adding what? 0.4 and 0.5. This is A and this is E. And 0.65 plus 0.5, how much? 1.15. 1.15 I got this one. And this I got by adding what? 0.5 and 0.65. So this 0.5 is nothing but what? C. 0.5 is C. This 0.65 I got by adding what? 0.3 and 0.35. 0.3 I got by adding 0.1 and 0.2. This is D, this is underscore. So this is the first. Now I got only one thing. So now I need to add what? These two I need to add. I will get only one thing. Okay, the finally now I got what? The finally sixth step. Okay, finally sixth step is what? I got sixth step. 1.15, 0.9, how much? 2.05. This 2.05 got. This I got by adding what and what? 0.9 and 1.15. So this 0.9 I got by adding 0.4. This is E and 0.5. 0.5. This is nothing but A. Okay. So the 1.15 I got by adding 0.5, this is C, and this is 0.65, and this I got by adding 0.3 and 0.35. 0.35 is B, but 0.3 I got by adding what? 0.1 and 0.2. So this is my final tree. Okay. So here 50% of the task is done. So this is what the Huffman tree we constructed. From this now we need to generate the what? Huffman code. For that what you have to do is simple. See, this is the root node. Okay, still see any number of characters are given. Still we get the one root we should get. Keep constructing the tree. In this example I had to suppose one more character is there, we get one more step. Okay, depending upon the character. Suppose here it ends only one root, here only will stop. Okay, that depends on the problem. So now we have got only one root. This root having one left tree, left child, right child, left child, right child. Now keep assigning the value to the left child or the right child, 0 or 1. Whichever the value you are using, fix it. Okay, suppose now in this case I am assigning here 0, left child 0, here 1. Similarly, now here also 0 no, here don't change. Okay, 0, left, right child. Left is 0, right child is 1. Left is 0, right is 1. Left is 0, right is 1. Done problem. Suppose you can, I will use, somebody can say, no sir, I will use 1 for left, 0 for right. That's fine. But once you fixed here, the same thing you need to follow. Okay. So I use this convention. So this is done. Now what you have to do, see, from this what I got, from this, now let us write. Okay, I will clear this to write all these things again. So now, first character is A, right? A. For A, where is A? A is here, right? A character A is here. See here. So now you travel from the root node to the character. See, if I am traveling from this one here, so then I will see here. If I am traveling for A, I am coming from here like this, right? So in this path, what is there? 0, 1. So this is the character for A. A is 0, 1. This is the code we are saying for A. Fine. Similarly, check where B is. Okay. So first I will write all the characters A, B, C, D, E, and then underscore. So we found for A. Let us check for B. Where B is there? See, B is there here. Now see here. Now for B, again from the root travel. Okay, from here like this. Okay, then like this, then like this. Now in this path, 1, 1, 1. 3 ones are there. So code for B is 3 ones. Okay. So next, where C is there? C is there here. C here. C. Okay. C you have to travel like this. So that is 1, then 0. So for C it is 1, 0. C is 1, 0. Okay. Next D. Where D is it? So D is here. So you travel from here. See 1. D is here. So okay. 1, 1, 0, 0. Again 1. See you have to reach here. See you have to reach like this, right? So 1, so again 1, 0, 0, double 1, double 0. So for D, double 1, double 0. Similarly for E, after that D, E, right? E. See, E is right for it. So here it is 0, 0. For E, it is 0, 0. Underscore is there here. Okay, see 1, 1, 0, 1. 1, 1, 0, 1. This is the code. See, here for A, 2 character code. For B, 3 character code. For D, 4. So that is what I called is Huffman coding is in variable length coding. That means whichever the character, see, which is according to this table, which character is appearing more, probability of occurrence is more. See, A and C is more probability. 50% probability. This is the most frequently occurred. So you should get what? Less length code. See what? See A and C, only 2 length. 2 character length. See here, which is the least frequently occurred character according to this table? D. D is 0.1, 10% of occurrence frequent probability of occurrence of D is only 10. So that is, so it should get what? Lengthy. Okay, see here, D. D is get 4 character. Length of this D is 4. So this is what the variable length coding. This is what Huffman coding. Now, see in earlier, when I show the example of high DAD, so that every character is having 8-bit ASCII value. But here it's not 8-bit ASCII value. See, it is only 2 A. For D, it is double 1. See, for DAD. For DAD, now how many characters I want to send? D is 1100. This is for D. A 01. Again 1100. So So totally 4 plus 4, 8, 10. So only 10 characters is enough to send dad. But at that time, it's not possible. 8, 24. 24 bit, now we reduce it to what? 10. So this is what the compression technique. Okay, so it's a lossless means, so now assume, so this is decode. For example, assume in your exam, they can ask, encode the text. Encode the text, let us take dad B. Okay, for example, dad underscore B. This you need to encode. Encode means what? Already I know the code of these characters. Simply replace these characters by this code. That's it. Okay, D. D is what? 1100. A is what? 01. D is 1100. Underscore is 1101. B is 1111. E is 00. This is the encoded text of that B. That means if you type this one, this will go. This bit will go. Okay. See here how many characters? 4, 2, 6, 10, 14. 14 plus 5, 19. Totally 19 characters. But if you use regular ASCII value, say 1, 2, 3, 4, 5, 6, 48 characters. Instead of 48-bit character, we are sending the same information with the help of 19 characters. So that means 29 characters we have compressed, 48 to 19. Okay, this is what the compression. So this is what encoding. Suppose assume in the exam, they will give one bit of string and you need to decode it. So how to do that one? See, now assume this is what encoded text they have given. Okay, this already is compressed. Now I have to decompress it. That means I need to see, this is the bit I have received. This is the encoded text. This I need to decode it. That means I have to convert it into the text. Okay, with these characters. How to decode it? So first check. Character by character. 1. Any one code is there? No. So 1. Not like 2 characters. 1, 1. 1, 1 is there here? 1, 1 is there? No, 1, 1 is not there. So let's take 1, 1, 0. 1, 1, 0 is there here? No, 1, 1, 0 is not there. See, 1, 1, 0 is not there for complete. Okay. No, 1, 1, 0, 0 is there. Yes, 1, 1, 0, 0 is there. So that means this is nothing but what? 1, 1, 0, 0, D. Next, again, 1 is there. No 1. 1, 1 is there. Not 1, 1. 1, 1, 0 is there. 1, 1, 0 not there. Again, 1, 1, 0, 1 is there. Yes, 1, 1, 0 1 is there. So this is nothing but underscore. So next, 1 is there. 1 is 1. 1, 0 is there. 1, 0 is C. So this is nothing but C. That means this is equivalent to what? D underscore C. This is what? Decoded. That means see, we can, without losing any of the information, we are able to retain the same data. Okay, that's what this Huffman coding, beauty of this Huffman coding. Okay, so and then another one useful property of this Huffman coding is whatever the code it will assign, we call it prefix code. So code assigned to one character will never be the prefix of another character. Okay, so for that I will give one more example. So assume this is the character A, B, C, D, 4 characters. Code for A is 0, 0. Code for B is 0, 1. Code for C is 0. Code for D is 1. Assume. Now, assume this is the encoded bit. This I have to decode it. Okay. Now, see. For 0. 0 what? C. So that means this one, this is C, 1 is D. This is one possibility. But I cannot. Instead of 0, I can take this 2 as what? A. This is what A and this is what? 0, 1. 0, 1 is B. It may be AB or maybe triple CD, or suppose for example I will take this as AA 00. Okay, again I will rewrite this again in order to understand, make it to understand. See now this 00 will take it as what? A. This 0 will take it as C. This one will take it as D. That means here is the ambiguity is there. Same code I am decoding as CCCD or AB or which is right. So that means this type of coding is wrong. That means where ambiguity. What is the ambiguity is? It's a code of C0 and that will be the prefix of A and B. This is a prefix of A and B. Similar, okay, that should not be there. That means whatever the code we assign to one character, that should not be the prefix of other characters. So hence this ambiguity will come. Ambiguity, confusion. So that confusion is not there here. See, for this, however, you will get always D underscore C only. You can decode easily. Okay, there is no ambiguity because whatever the code assigned to any one character, that is not the prefix of other characters. Okay, see, it is 0, 1. 0, 1, this is no other character assigned 0, 1 as a prefix. 0 1 is there anywhere? No, nothing. Similarly, triple one. Triple one is not at all the prefix of any of these things. Similarly, 1 0. See, there is no 1 0. 1 0 is not there. 1 0 is not there. Similarly, 0 0. 0 0 is not there. See, 0 0 is not there. Prefix. So, this is the beauty of the Huffman coding. So, Huffman coding is a lossless compression technique and it is a variable length coding technique. Okay. So, hope you people understood the concept of this Huffman coding. Thanks for watching. If you have any questions, please write it in the comments. Thank you. Thanks for watching.